This is a demonstration of pairwise coordination diagnosis and the field implementation. First, let us look at pairwise coordination diagnosis. We start with the probabilistic time-space diagram in both the southbound and northbound directions, which are generated by the estimated traffic state. The current offset is the difference between the start of the cycle and the reference point. We can visualize how a new offset will impact coordination by adjusting the additional offset toggle bar. Additional offsets can be added to the existing signal timing plan to change the traffic signal coordination. In pairwise coordination diagnosis, we consider two intersections. It is important to analyze potential offset changes in both the southbound and northbound directions. The current green start implemented at this intersection is shown here. Let us predict what will happen if we add an additional offset of 26 seconds. The bottom left figure reports the total delay prediction for different additional offsets. The bottom right figure reports the number of stops. The southbound performance prediction is shaded blue, and the northbound performance prediction is shaded in orange. The green dashed line in both figures indicates the current additional offset reflected in the probabilistic diagrams. As the additional offset changes, the green dashed line indicates the predicted hourly delay and total number of stops. The optimal additional offset in terms of the minimum delay and number of stops occurs at an additional offset of 33 seconds. Considering the existing timing plan, we can visualize the coordination optimality gap as the difference between the current performance and the predicted performance at the optimal additional offset. The probabilistic time-space diagram allows us to see that at this additional offset, most of the trajectories that depart the upstream intersection right after the green start directly pass the downstream intersection without stopping, hence the reductions in delay and the number of stops predicted by the model. Pairwise coordination diagnosis is performed for every two adjacent intersections through the entire corridor. We now discuss the field implementation. This is a before and after comparison of the coordination optimization. Aggregated time-space diagrams for the midday time of day in both directions using data from 3 weeks before the signal retiming are shown here. The signal retiming included offset changes at 3 intersections. These are the aggregated time-space diagrams from 3 weeks of data after the signal retiming. The average number of stops and delay was reduced in both directions. The red boxes highlight areas of poor coordination before the signal retiming. Vehicles from the upstream queue were arriving at the downstream during the red light. The improvements in coordination at these areas after the signal retiming are shown within the blue boxes. Vehicles from the upstream queue directly passed the downstream intersection. This resulted in a reduction in the number of stops. We can also analyze the behavior of a typical vehicle as it travels through the corridor. The red line traces a typical southbound vehicle path before signal retiming. This blue line traces a typical vehicle path for most vehicles after signal retiming and reflects the reduction of delay experienced by the vehicle. A minority of vehicles follow a path traced by this blue line. These lines trace the differences in vehicle paths before and after signal retiming in the northbound direction. It is very easy to observe the reduction in the number of stops between these two paths.